All right, so welcome to this part of this topic. This is a binomial probability distribution. Now, maybe the name itself can guide you into the kind of experiment we'll be referring to here. Look at binom. So bi signifies two. So one characteristic that we're going to mention of binomial distribution is that it involves variables which have two possible outcomes. Variables which have two possible outcomes. For instance, when you inspect an item off the production line, the item may either be defective or not defective. If the variable of interest is the gender of a person, then the gender is either male or female. When you sit for an exam, the results are either you pass or you fail, and so on and so forth. So those are examples of what you're calling binomial variables. But there are four conditions that must be satisfied simultaneously for any variable to be called binomial, or for any distribution to be called binomial. So let's start by saying that the binomial probability distribution is applicable. The binomial probability distribution is applicable in situations where an experiment is applicable in situations where an experiment consisting of a certain number of trials satisfies all the four conditions below. All the four conditions below. So the following four conditions must be satisfied for any experiment to be called a binomial experiment. Number one is that the number of trials must be fixed and finite. So we say that the number of trials must be fixed in advance. Before the experiment begins, you must know how many trials you are going to run. And then it must also be a finite number. The number must be finite, okay? Must be known, must be countable. So this number is usually denoted by n. So in short, we are saying that n must be finite and must be fixed in advance before the experiment begins. Okay. The second condition that must be satisfied is that every trial results in in only one of two possible outcomes. Only one of two possible outcomes. Okay, so every trial has two possible outcomes, but only one of them happens. You cannot have both occurring. Eh? So these two outcomes are called, sometimes we say they are labeled, success and failure outcomes. So one of the outcomes is called a success outcome. And usually this is the outcome that we are interested in, while the other outcome is called the failure outcome. That's the one that we are not interested in. For instance, if you are tossing a coin, let's say 100 times, and your interest is the number of heads that will be observed, then H or head will be your success outcome and tail will be your failure outcome. So these labels do not have a literal meaning. They're just labels. They're just labels. They are not literal names. So we're saying that we have the success and failure outcome, and they are mutually exclusive. They are mutually exclusive. So these two outcomes are mutually exclusive. They are mutually exclusive. Mutually exclusive means that they cannot occur simultaneously in the same trial. That means once one of them happens, it means that the other one cannot happen or has not happened. They are mutually exclusive. Okay, so they are both mutually exclusive and collectively exhaustive, meaning that these two outcomes represent the totality of all the possible outcomes in that given trial. So they are also collectively exhaustive. That means that if you sum the probability for each one of them, if you sum the probability of the two of them, you will end up with 1. You'll get 1. I'll mention that a little bit later. Number 3, the third condition that must be satisfied is that the probability of success, or failure, the probability of success or failure remains the same in all the trials of the experiment. The probability of success or failure remains the same or remains equal in all the trials of the experiment. So this probability is denoted by small letter p, while the probability of failure is denoted by small letter q. So we use letter P and Q to denote the probability of success and failure, respectively. And because of what I said earlier, that these two outcomes are collectively exhaustive, we say that P plus Q is 1. So for every trial, P plus Q is always equal to 1. Now, the fourth condition that must be satisfied for a distribution to be called binomial, or for an experiment to be called a binomial, is that the outcome of every trial, must be independent. The outcome of every trial must be independent of the outcome of every other trial. Of the outcome of every other trial in the experiment. So in short, the trials are independent. Okay, so independence is a very important concept here. Okay, when we talk about independence, I want to define what is independence. Independence. We say that two events, A and B, are said to be independent. They are said to be independent if I'm going to give a mathematical definition. Probability of A, given that B has occurred, if, for instance, the probability of A, given that, this is conditional probability, probability of A, given that B has occurred, is the same as probability of A. That just means, in layman's language, that means that the occurrence of B does not in any way affect the occurrence of A. And probability of B, given that A has occurred, is equal to probability of B. So that means that the occurrence of A does not in any way affect the occurrence of B. So that's the definition of independence. So for two events, A and B, to be independent, and that must be true. That must be true. Then we say that if A and B are independent, if A and B are independent, then the probability of both occurring, that is, the probability of A and B is the same as, which is, you can also write it like this, is the same as probability of A times the probability of B. It's the same as that. So if you revisit the example or illustration, sorry, the illustration on tossing of two coins, if you revisit the illustration on the tossing of two coins, and you want to find, because we're assuming that the tosses are independent, okay? The outcome in every toss is independent of the outcome in the other tosses. So in such a case, you can say that the probability of getting a head followed by a head, or head in the first toss and head in the second toss, is the same as probability of getting head in the first toss, the same as probability of getting a head in the first toss, times probability of getting head in the second toss, which is the same as 1/2 times 1/2. So that's why somebody told me the answer was 1/4, because we assume that the tosses, or the outcomes, when you toss a coin or a coin twice, the outcomes in every toss is independent. So independence is the last condition that must be satisfied for any experiment to be called binomial. So those four conditions must be simultaneously satisfied, all of them. So you cannot skip one of them. All of them must be satisfied for any experiment to be called a binomial. Okay, so examples of binomial experiments. Examples of binomial experiments. And we have some examples which have been given in our notes. So we may want to look at them. So examples of binomial experiments include these ones. Number one, when you roll a die, so you will write these ones in your notes. When you roll a die, you either get a 6 or you do not get a 6. Okay, you know that a die has six sides like that. So you may have 1, 2, 3, 4, 5, 6. So you either get this side or this face showing up, or you do not get a 6 showing up. So if you define it like that, when you roll a die, you may end up with a binomial experiment. Okay. The same case when you toss a coin. When you toss a coin, either the heads come up or the tails come up. So that's again binomial. The gender of a child is either a boy or a girl. When you inspect some items off a production line, then every single item is either defective or not defective. So those are examples of binomial experiments. You can check for others maybe in the textbook. So you're going to write those ones. So see class notes. See class notes. Okay. So the next thing, I want us to move to the general binomial experiment. So the examples that you've given up, they are very specific. Those are very specific binomial experiments. So I want us to come up with a general experiment, so that at the end of the day, we'll end up with a formula that will be able to represent, or a formula for the binomial distribution. Okay. So in a general experiment, where each trial has just two mutually exclusive outcomes, we can define we can define probability of success this way. We can just say that probability of success is equal to P, and probability of failure, we can define like this. Probability of failure is equal to Q. And then we need to note that P plus Q is equal to 1 because they are collectively exhaustive. Okay. So let's look at the first trial. The first trial of a general binomial experiment. The first trial of a general binomial experiment. And we shall be, remember, we need to come up with a sample space so that we assign probabilities to each of the possible outcomes. So I'll be using a tree diagram to enumerate the sample space. So if you have a binomial experiment with only one trial, you'll end up with a tree diagram looking like that, where this is success or failure. I'll be using S for success and F for failure. From what we have just said, and I want to hear from you, what is the probability of success in this binomial experiment? What's the probability of success? You can just unmute yourself and say what you think.
1/2.
1/2. Someone else? Somebody else? Now 1/2 is possibly the probability of getting a head or tail if your binomial experiment is tossing a coin. But here we are not tossing a coin. We are doing a general experiment. And the answer is up here. When you toss a coin, when you conduct a general experiment, general binomial experiment, the probability of success is this. You can see that, it's P. And the probability of failure is this, Q. Okay, so the sample space, so let's list the sample space. You can get S, you can get F. So let's have the probabilities. The probability of getting an S is P, and the probability of getting a an F is Q. I can convert this into, I can let me do this. Let X be the number of successes. So that's our variable of interest, X, the number of successes observed. So number of successes, I just need to count the number of S's. So here we have one S. Here we have no S, so 0. So the number of successes when you have one trial is either 1 or 0. Okay, so from there we can come up with a table. Let's create a table here where this is our X, number of successes, takes the values 0 or 1. Then we can have the probabilities. The probability that there is no success or you have 0 success when you conduct a binomial experiment with one trial. The probability of no success is Q. And the probability of 1 success is P. So here, let's just do this, P plus Q. We know the answer is 1. But the sum of all the probabilities there in the sample space is P plus Q, which you know is 1. Okay, so let's move to a binomial experiment with 2 trials. So binomial experiment with 2 trials. We're going to represent that again using a tree diagram. So we shall have the first trial gives either success or failure. The second trial gives success or failure. Here also success or failure. So we have 4 possible outcomes. 4 possible outcomes. And we said that the probability of success remains constant throughout the experiment, So this will be P, this will be P, this will be P, this will be Q, this will be Q, this will be Q. And then the sample space. So let's enumerate the sample space. You can get SS, you can get SF, FS, and finally you can get FF. Okay. The probabilities, the probability of getting SS, we said that the trials are independent. So the first trial is independent of the second trial. So the probability of getting S followed by an S is P times P, which is P squared. The probability of getting S followed by F will be PQ. Using the same logic, we have QP. I'm going to call it PQ again. And the probability of getting F followed by F is Q times Q, which is Q squared. Our interest is the number of successes. We count the number of S's in every outcome. And the first one we have S and S, so those are two S's. In the next one we have one S. In the third one we have one S. In the last one we have zero S's. We have zero S's. So with that, we can come up with a table to represent that. So this is a number of successes ranging from 0 to 2, taking the whole numbers. So number of successes takes the values 0, 1, or 2. Then the probabilities, probability of having no success is the same as probability of having F and F, which we have said is Q squared. Okay. The probability of getting 1 is the same as probability that X is equal to 1 success. Probability that X is equal to 1 is given by probability of SF or probability of FS. So we add those two probabilities, which is PQ plus PQ, which is 2PQ. 2PQ there. Then finally, the probability of getting 2 successes, or probability that X is equal to 2, which is equal to probability that probability of SS, which is given by P squared. So you may want to write this. I want to write this. You will find out later why. P squared, I'm summing them. I'm deliberately starting with P, plus 2P Q plus Q squared, okay? Maybe some of you can see something there. Then finally, let's look at a general experiment with 3 trials. A general binomial experiment with 3 trials. General binomial experiment with 3 trials. So we are going to have a tree diagram with 3 levels of branches. So I may need some bigger space here. So the first trial gives me success or failure. Second trial gives me success or failure. And even here, success or failure. The third trial gives me success or failure. Even here, success or failure. Success or failure. Success or failure. So, and then the probability of success and failure remain the same throughout the experiment. So this is PQ, 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 P, and Q. All right, then the sample space. The sample space. So here we have SSS, SSF, SFS, SFF. This is FSS, This is F, S, F. And this is F, F, S. And finally F, F, F. And probabilities, remember these events, these trials are independent. So I just multiply the probabilities. So this will be P cubed. This will be PPQ. So this is P squared Q. This will be PQP. So I can PQP, sorry, which will give me again P squared Q. I'm deliberately starting with P. And this will be PQ squared. And this will be P squared Q. This will be PQ squared. This will be PQ squared. And this will be Q cubed. That will be Q cubed. I hope that is okay. Hope those probabilities are okay. Yes, then we can have the number of successes. Number of successes. So you just count the number of S's in every outcome. In the first one, we have 3 S's. Here we have 2 S's, 2 S's, 1 S, 2 S's. This is 1 S, 1 S, and no S. So the number of successes ranges from 0 to 3, taking the whole numbers in between there. So our probability distribution will look like this. Number of successes, we'll take the value 0, 1, 2, 3. Then probability, let's start with the probability of no success. Probability of no success will be the last one. This is it. This is it. This is the probability. So this will be Q cubed. The probability of one success, that is probability that X is equal to 1. So just check where X is equal to 1 like that. Where X is equal to 1. Then you add those probabilities. You add those probabilities. So this is PQ squared plus PQ squared, again, plus PQ squared. So this gives us 3PQ squared. The next we move to when X, the number of successes is 2. So we're going to add the probabilities when X is equal to 2. So the parts I'm taking, those 3, you add those probabilities. And as you can clearly see, it will give you 3P squared of Q. If you have a question, please ask at any time. And then finally, the probability that X is equal to 3, that we have 3 successes, is given by this guy here, which is P cubed. P cubed. So let's get the total there. When you add these guys, when you add these 3, not 3, there are 4, you will get, I'm starting with P deliberately, P cubed plus 3P squared Q, 3P Q squared plus Q cubed. Maybe some of you can see this. If you look at the second scenario and this scenario, you should be able to see something. Okay, so now I want us to generalize, because it is through this generalization we are going to get the formula that we shall be using for binomial distributions. So if you have not seen anything so far, so let's recall this. If you take, number 1, if you take P plus Q, you raise to power 1, what do you get? If you take P plus Q, you raise that one to power 1. What do you do when you expand that? You get P plus Q. Okay, you get P plus Q, just like what we have up here. You'll get this. If you take P plus Q, you raise to power 2, P plus Q, what do you get? This is the same as P plus Q multiplied by P plus Q, which gives you what? this binomial expansion, huh? You know this is binomial expansion. You get p squared plus 2pq. Okay, you get that, which is what we have up here. It is what we have here. Okay. Then, so this is p squared plus 2pq. Now, finally, if you do this, you take p plus q, you raise to power 3. It's the same as taking this, the same as p plus q squared multiplied by p plus q. So take this guy here, multiply by p plus q. So you'll end up with p squared plus 2pq q squared plus q p squared plus 2pq plus q squared. So if you expand this, you're going to get p cubed plus 2p squared q plus p q squared. Then crossing the other side, you have p squared q plus 2pq squared plus q cubed. Then if you group like terms together, this one is alone, so we'll get p cubed. Then 2p squared q, you add to this 2p squared q plus 1p squared q, you get 3p squared q. And if you combine this term here with this term here, you'll get 3p, and then this one is alone, so you'll get q cubed. So that's what we have here. So this is p cubed plus 3p squared q plus 3pq squared plus q cubed. And this is quite similar to what we got up here. It is quite similar to what we have here. Okay. So now you know what is happening. You know what is happening. So this is when we got this, when we had one trial, when we had 2 trials, when we have 3 trials. That means when you have 4 trials, you can also get the required total probability. Okay. If you have 5 trials and so on and so forth. So what we do now, we generalize. So we move all the way to p plus q power n. So what do you get? So if you're able to get that expanded formula there, you will end up with what we call the binomial expansion. The binomial expansion. And that is what we shall be using as our binomial formula. So you can check this one at home, but you will notice that as you continue expanding, especially if you keep, if you note the coefficients of these values, this is 1. You can imagine, let me shed some light here. I can write this as p cubed, q power 0, plus 3p squared, q power 1, plus 3p, q power 2, plus p power 0, q cubed. So I can write it like this. And then I keep on playing around with the powers in such a way that the powers will always be summing up to 1. This is power 1 also, okay? So like that. Then some coefficients here. There are some coefficients here, which will be changing from one scenario to another, or from one power to another. So if you go to power 4, you will still have the pairing of p and q, but now these coefficients will keep on changing. So if you continue like that, we'll see some pattern. You will see some pattern. And that pattern can be generalized into this format. So if you take p plus q power n, you will get with a summation. As you can see, we are summing up some items. It will be a summation of n combination. Let me clear this space. If you continue to power n, you will observe something like this. Delete that. So the final answer will be given by this. P of X Q n minus X, where this is a constant. These are constant. These are constant. It's a number. It's a number, which we will be getting it from our calculators, showing the number of ways of choosing X from n items. Let me put it like that. It's a counting technique called combinations. The number of ways of choosing X items from n items. So you'll be using your calculator to obtain that, but there's a formula which you may not be interested in now. Then of course, P is the probability of success as defined earlier. So P is the probability of success. Q is the probability of failure. Then X is the number of success outcomes. And N is the number of trials. Okay. So for this constant, I don't want us to talk so much about it, but we'll be using our calculators to obtain these. So we'll be using a calculator to obtain that. If you check your scientific calculator, there's a function written like this. If you check your scientific calculator, you'll find that in most of the cases you need to shift. You need to shift for you to get that value. For instance, you may want to look for the number of ways of choosing 2 successes out of 3 trials. So that means the number of trials is 3 and the number of successes is 2. So you will press 3, then you press that function in your calculator, then you press 2 followed by equal sign. Maybe the answer is 3. Okay, I think the answer is 3. Okay, and so on and so forth. You can try for many other values of n and x. You notice that the value of x, you notice that the value of x must always be less or equal to n. For that function to work, the value of x must always be less or equal to n. Okay. So now, finally, conclusion. So when using the binomial distribution, where n is the number of trials, comma, x is the number of successes, and P and Q are the probabilities of success and failure. That is our binomial distribution. The probability of getting exactly X number of successes is given by, so we modify the above formula, binomial expansion to get this probability that the number of successes is equal to that is given by n choose x p of x q n minus x. So that's the formula that we use in binomial distribution. So remember we said that a probability distribution comes in the form of a table or a graph or a formula. So this is a formula for binomial distribution. That's a formula for binomial distribution. Well, of course, this is as explained above. This will be a constant that we'll be getting from our calculators. So any questions? I want us to